Hello, in this video I'll explain to you the magnetic field which gets created around a straight wire when a current flows through it. So a current is flowing the direction shown on the red wire and the magnetic field is getting created around the wire and they are concentric circles and that's why the arrows are rotating. If you look at a still image and if you look at a horizontal plane, then as per the right hand rule, and you can see a right hand in this video, the thumb shows the direction of the flow of current and the curled fingers show the direction of the magnetic field that's formed. So on the other side of the wire, the magnetic field shown by green arrows are pointing downwards, and on the near side as shown by the fingers, the magnetic field is pointing upwards. And you saw the animation as well, and at any point on that concentric circle you know what will be the direction of the magnetic field. Having said that, in this sketch I have shown you a very simple arrangement with a DC battery where the current is flowing only in one direction. If you have an AC current source, the current will reverse itself, in which case the magnetic field will also reverse in its direction. Here is another view of that arrangement where you can appreciate the direction of magnetic field that's going into the plane of the paper, so to speak, in a 2D language, and the arrows that are pointing upwards are said to be coming out of the plane of the paper. And you can see I've just moved the hand a little bit in front, and you can see that the fingers are very clearly aligned with the direction of the magnetic field. We now draw a textbook 2D representation so that we can get the equation for magnetic field. We draw the exposed part of the wire as Mn. You can see here it is the same as the exposed length of wire that you saw in the sketch and animation. If the wire is insulated heavily, the insulated portions will minimize the magnetic field, and sometimes we can have even no magnetic field. If the wire is a bare wire, aluminum or copper, then when the current flows through it, it will set up a strong magnetic field around the wire. So let's select a point P in space, which is shown here, and the direction of current is shown by the pink arrow. The magnitude of the current is I, and therefore using the thumb rule, the direction of the magnetic field at point P is into the plane of this slide, and at the opposite end the direction of the magnetic field is coming out of this slide perpendicularly. The distance of the point P from the wire is OP equal to D, and we now select a infinitesimal length of wire called DL using differentiation methods, and that DL is at a length L from the point O. The DL subtends an angle theta with point P because DL is quite far away from point P, and the length of the wire, which is Mn, has two angles. The lower point M subtends an angle θ1 with point P, which is an acute angle. The other edge of the wire is N, that subtends an obtuse angle θ2 with point P. With that, the magnetic field at P due to dl only is an infinitesimal magnetic field dB, is equal to mu0 by 4 pi into I into dl sine theta by r squared. The dB is therefore proportional to the current I. It's proportional to a constant mu0 by 4 pi. It's proportional to the dl sine theta, and it's inversely proportional to the radial distance, the term r squared. dB was an infinitesimal magnetic field, but to get B we have to integrate dB, and when you do that all over the length Mn, so you can imagine many dLs placed all over the length Mn, then we get the equation B is equal to mu 0 by 4 pi, which is a constant by itself, into current, proportional to current, divided by d, the distance between O and P, into cos theta 1 minus cos theta 2. Here the unit of B is in Teslas. Mu 0 by 4 pi is a constant, which is Tesla meter by ampere. That's equal to 10 to the power minus 7. And the i's and the d's and the theta 1 and theta 2 depend upon the particular case. We now derive the equation for a very long straight wire. Because it's very long, Mn is not finite. So in this sketch that we have drawn, there is no M and there is no N. The point P is there as usual. The point O is there. We have DL at a length L. And what happens here is that the length of the wire is so long that when you draw the line from point P to the edge of the wires, theta 1 almost tends to 0. And the angle theta 2 tends to 180 degrees. So you can imagine a wire which is as long as the whole room where we are sitting. Due to that, when B is equal to mu 0 by 4 pi into I by D into cos theta 1 minus cos theta 2, cos theta 1 becomes cos 0, that's 1, and cos theta 2 is cos 180 degrees, that's minus 1. So that becomes 1 minus minus 1, that's 2. So mu 0 by 4 pi into 2 becomes mu 0 by 2 pi, and therefore you get magnetic field B is equal to mu 0 by 2 pi into I by D. This is just a simplification of the original equation. If you have any queries, feel free to write back in the messages. Do subscribe to our YouTube channel, share it with all your friends. You can log in free to our websites depending on whether you're in India or abroad. Login is free. The course is paid. Have a great day and see you soon.